Year 11. I have had a request to go through question 5 from exercise 9H, and actually this is the second request I've had, so I'm recording this, so if you get a problem with that question, you can have a look as well. So let's just take a quick look at the question. It's this one here. F of x is e to the power 2x sine of 2x with x from 0 to pi. And it says use calculus to find the coordinates of the turning points. So turning points are your maximum or minimum points. So that's when the gradient is 0. So we'll differentiate once and set it equal to 0. Then show that f double dashed of x is this, so we'll differentiate it again, try and get that. And then we'll determine which is a maximum and which is a minimum by substituting the x value in. If it's negative, then it's a maximum, a local maximum, and if it's positive, then it's a local minimum. So here's what we'll be using. If dy by dx is 0 at a given value of x, and d2y by dx squared is less than 0, the point is a maximum point. Now this means a local maximum, so you could have a graph that kind of goes like this. You can see here that this minimum is actually above, it's got a higher value than this maximum, but we call this a local maximum, and this is a local minimum. So really, these should be saying local and local next to them, but just to make that clear, you can also have a global maximum, so this would be our global max here, assuming that this graph doesn't go up any higher outside this domain, and this might be our global minimum, but it's kind of hard to tell. Maybe the global minimum is over there, or maybe there isn't a minimum because it keeps going down forever, if it keeps going there, for example. Okay, so let me just copy down the important info and we'll get going. So f of x is e to the power of 2x sine of 2x, and x is between 0 and pi, strictly between 0 and 0 and pi. So that's our domain, and that will be important. Now, here we have a product, so we're going to use the product rule. If y is uv, then y dashed is u dashed v plus uv dashed, where dashed means the differentiated function. We've got the added sort of trickiness here that these aren't simple functions, these are actually composite functions, e to the power 2x. Now, I'm not going to go through how to differentiate each of these in detail, but if you need to, you would use the chain rule. I'm just going to tell you that here e to the power 2x stays the same, and then we multiply by the differential of 2x, and here sine differentiates to cos, so it's cos of 2x, and it's also multiplied by 2 because I'm multiplying by the differential inside. If you're not sure on that step, then pause here and work through both of these differentials using the chain rule. So the chain rule, a little reminder, is dy by dx equals du by dx times times dy by du, but actually usually these are written around the other way, but it doesn't matter. Okay, so let's carry on with the product rule then. So y dashed, or here I should use the notation given in the question, so f dashed of x is, differentiate this one, leave this one alone, so essentially it's these two multiplied plus these two multiplied. So I get 2e to the 2x sine of 2x plus, I'll put that 2 there, 2e to the power 2x cos of 2x. So that gives me 2e to the power 2x sine of 2x plus cos of 2x. And for turning points, f dashed of x equals 0. So that tells us that 2e to the power 2x sine of 2x plus cos of 2x is 0. Now, 2e to the power of 2x is never 0. 2 is never 0, and e, our function, is never 0. y equals 0 is actually an asymptote for this graph. I just know that from a sketch. But also, if you tried to solve this by, let's ignore the 2 for a moment, if you tried to solve that by taking logs of 0, it wouldn't work. You'd get an error function on your calculator. So this doesn't give us any, this never is 0. So if this times this is 0, it must be this side that is 0. So if this side is 0, I get that sine of 2x plus cos of 2x is 0. I'm going to rearrange that, put the cos over the other side. I'll show you the steps. Equals negative cos of 2x, and then divide both sides by cos of 2x. So I get sine of 2x over cos of 2x equals negative 1. Now this, using the identity that you should know, is tan of 2x. So I need tan of 2x equals minus 1, where my domain is from 0 to pi. I think it's easiest here to just use a substitution like let theta equal 2x. So I'm actually just simplifying the equation. I just need tan of theta is minus 1. And my new domain, because theta is 2x, my new domain will be from 0 to 2 pi, because I'm basically doubling everything. You could write it first of all like that, just to make it really clear. So I want to know, when is tan theta negative 1? Now, the natural thing to do here is to put it onto your calculator. So open this up. I need, if tan of theta is 1, then theta is tan inverse of negative 1. And you can see I've typed that here. I get negative 1/4 pi. Now remember, this question is in radians, so it's telling me that this is negative 1/4 pi. Now that's a bit annoying because that is not within this domain. And my calculator's only really going to give me one answer if I do it like that. So I'm going to try a different method, which I can use on my graphical calculator, which is to draw tan theta. So I'm going to sketch. Hang on, I don't want to do that. I want to go to into my graph. So I'm going to put in here tan. There's no theta button, I'll have to use X. And let's draw that. Okay, now I'm going to change the window so I can actually see what I want. So I want this to go from 0 to 2 pi, and tan does not stay between minus 1 and 1. I actually know that the graph of tan looks more like this. It's got these asymptotes here, so I'm not going to go up to plus and minus 1. I'll go up to, let's say, 10 and minus 10. I don't know what I want to do there. Can we say 0.1? I'm not sure what a dot means, to be honest. So negative 10 and 10. Let's see if that gives us something that looks reasonable. No, it doesn't. Let's just check the window again. Right, so I think when I put in the dot it must have rejigged that max x, so let's try that again. Okay, now actually I'm just going to take my minimum scale down, but I'm going to take it down to minus pi so we can see where that first answer was coming from. So if I put gsolve, actually I want to intersect it with, right, rewind. The best thing for me to do is actually to put in another line that says y equals minus 1, because I want to know where are the intercepts with minus 1, so let's draw that. Alright, here's the line minus 1. This is below our domain, but that point there is the point. It's coming up as a decimal, but this is actually minus 1/4 pi. That's the answer that our calculator was giving us when we just tried to solve it algebraically. But we don't want that one. It's the reason we're getting that one from our calculator is because it's the nearest one basically to the origin. We want the next one up, which is given on our calculator as a decimal. But knowing that the domain or the period of tan repeats every 180 degrees, which is equivalent to pi, it just repeats every pi, it kind of does this little twiddle. So if one of our answers was minus a quarter pi, the next one up will be that plus pi. So that will be 3/4 pi. This is one of the problems with doing it on a calculator like this, is that you won't get an exact answer, and you need to be able to get an exact answer. It would be okay to put 3.56 or 2.36, but only if you didn't want to have it as an exact answer. You don't want to be in the position where you don't know how to get the real answer. Okay, and then the next one is one up. We just add pi again. So add on another pi, you get 7